Udi Peled, multi-party computation, toy example and application to blockchain. Udi?
יש Fireblocks בקהל. Hi, I'm Udi Peled, cryptographer, and Fireblocks and the master key VC. And okay, this is a very different type of talk. I don't have any nice exotic pictures. I'm not going to sell you anything. I'm just going to present to you a bit of mathematical tricks, but hopefully without any math and cryptographic ideas, I would say. So, okay, multi-party computation, it's a topic in cryptography. I'm going to see an example for it, like a really simple example without any algebra. And later we'll talk about applications to blockchain with a bit of algebra, and we'll see how it goes. Very basic. But first I want to give you a taste of cryptography, and then we'll talk about the other stuff. Okay, so let's dive into it, and feel free to ask questions along the way, I think. It's right before lunch, so, you know, it's, you're postponing your own lunch, so if you ask questions, so, you know, take it into care. Okay. So cryptography, I want to talk in a high-level kind of a description. When I started learning cryptography, I mean, I asked people, or people asked me, like, what is cryptography? I told them, you know, I don't know, encryption, decryption, like examples. But really, when I come to think about it, what is cryptography? Is knowing how to work with secrets, okay, or the science of working with secrets. And let's see a few examples for it. So encryption is just one way of working with secret, right? You want to hide your secret, you encrypt it, you can put it whatever, you know, on your email, you publicize it or whatever, and you know that the ciphertext, the encrypted secret, doesn't reveal your secret. So that's one type of working with secrets. But another thing is that more related to blockchain is digital signatures. You're saying, I have a transaction, the transaction is not a secret, right? It's very public, everybody should see it, should verify it on the blockchain, but I want to use my identity, okay, this relates to Web3 thing, I want to use my private key, which is my identity, to approve this public transaction. So if you think about it, it's not exactly like encryption. It's I approve something which is public, but using my secret identity, or maybe, you know, private key, which should be kept secret. So it's a different like aspect or different tool in cryptography. Which again, relevant to blockchain. Another thing which is gaining popularity in the industry in recent years, also relating to blockchain, we won't talk about it, but it's an interesting topic to talk about, zero-knowledge proofs. I have a secret, okay, this secret you can think about, let's think about it as a number or something. I have some number that I don't want people to know, but I want to convince the world that my number is limited, is like at most 10,000. So I can prove to you, I can generate a mathematical cryptographic proof that I publish to everybody to see this proof that everybody are assured that my secret number is at most 10,000 without revealing the secret. Again, a secret should be kept secret. Again, very different from encryption, which is just say I hide the secret. I reveal something about it, but without really revealing it. It's a cool tool which gaining a lot of popularity, lots of use cases in the real world recently. And what we're going to talk about today, multi-party computation. Okay, this is the phrasing, but distributed computing of outputs using secret inputs. It's don't look at it. Okay, we'll see an example for it right now, which explains what is Mpc, and hopefully it will give you like the feeling. We'll go back into the general definition after the example. I like to start with an example. You get the feeling of it, and then more general definition. Okay, so everybody likes Alice and Bob. Okay, so now so this is, I called it a Tinder problem, but you know, maybe, by the way, this example I took from Yehuda Lindell, the professor which is an expert in MPC, and I kind of like expanded on it, on his example. So Alice and Bob, maybe a better name for it will be like speed dating. I don't know what you call it, like, you know, they sit in front of each other, and they want to say, do I like the other person or I don't like him? Okay. And do I have a match with him or not? Okay. And the only thing is that they want to be, yeah, here it is. They want to only the result of the match to come as the output. So that if one of them dislikes the other, or both dislike each other, we don't necessarily want them to reveal who's the one who liked and disliked. So if Alice liked Bob, and Bob disliked Alice. We want them to know there's a mismatch, but Bob shouldn't know, or Alice, who did I say disliked? Bob. If Bob disliked Alice, it doesn't necessarily need to know that if she liked him or not. Like it can cause him some, embarrassment that he's trying to avoid. Right? You only want to know there's a mismatch with hiding really the secret input. So if I relate it to cryptography, so they have like a secret input, a like and a dislike, like a Boolean value, let's say. And they want to reveal the result of it. Okay, and it's really, I think it's almost almost a practical problem that Tinder kind of solves. When you send your preference to Tinder, right, or something, and the server, the centralized server of Tinder, tells you, okay, there's a match or mismatch, but it doesn't tell you about the ones that told you I don't like you, right? It just tells you, look, there's a match, or you didn't match, like move on. So it's kind of like we already have a solution for it, which is trusted. But I want you to feel like the problem, right? You really want to avoid revealing your input to avoid uncomfortable situations, I would say. The goal of MPC, or in crypto in general, but specifically MPC, is to avoid the trusted party. Because now we have a trusted server, okay? Or let's say they both go to their friend, they tell their friend, look, I like him, I don't like him. But this friend is a single point of failure that if somebody, tries to get this secret data out of the friend, so of Tinder, somebody hacks Tinder's server, maybe they can get this secret data. So now we're talking about something which is kind of like, okay, just like and dislike. But later this secret data can be private keys. It can be, some private information that you don't want to be leaked. These inputs, which are, it's very like a toy example of like and dislike. So we're trying to hide it. We're trying to get rid of the trusted party that does the computation for us. How? So we just allow them to interact with each other. Oh, sorry? Yeah. We just allow them to interact with each other. No other party which is, can, let's say, know the secret or know handle the private data. So we're going to see like a really physical example now with playing cards, ace and king, really like, like a deck of cards, to achieve this goal of revealing if there's a match or there's a mismatch in the preference. And if we had more time, I'll really give it to you as an exercise, like to think about, or people coming up with ideas, how would you do it? Like, or you can use also pen and paper, maybe write something, give it to the other party, but how do you reveal your preference without revealing it, right? It's kind of like it's a problem. I hope that everybody feel the problem, like, okay, like I see somebody do like this, okay, yeah, oh, okay. So there's a real problem here. We're going to use cards to simulate like an MPC protocol and we're going to talk about like more general later. So this is what I do. Okay, so Alice, so we have just two cards, ace and king, and Alice puts them in the order according to her like or dislike. If she likes, she puts it king ace. If she dislikes, she puts on the table, right, ace king. And Bob does kind of like the reverse. Okay, if he likes ace king, if he dislikes king ace. Okay, until now we didn't do anything. All of this is, everybody does it to himself, right? He hides it from the other party because he doesn't want to reveal his preference, right? Like or dislike. Now they turn it upside down, so now it's completely hidden, okay? They don't see, now you can put it in the public, right? On the table that both can see, it's hidden, their preference. You put an ace in the middle, okay? This is both of them look, okay, it's an ace, okay, nice. And you flip also this ace, okay? Now what's hidden underneath? Let's think about it. Like they don't reveal it immediately. There's another step I will talk about later. These are all the options, right? If you think about it, if there's two likes, this is the order of the cards, right? You can verify. And the other options, you can also look, verify. Unless I did a mistake, right? I think these are all the options of preference or match or mismatch. Okay, until now, any questions? Okay. And the whole point of this protocol, okay, of this scheme to put the cards, is to notice that, okay, in my mind I had a laser pointer, but here I have a finger, okay? So to notice that these three orders are pretty much the same. Like there's something that really distinguishes the first one from the others. So what distinguishes them, or what's the same about this order? If you take this card and you put it at the front, you get this order. Right? So if you cut the deck, I'm going to talk in poker terms or whatever. If you cut the deck here and move only this card to the end, you get this order. And if you take this order and you cut, I think, these two and put it at the end, you get, put it at the start, sorry. Put it here, you get this order. And the same here, you can cut this and get the other ones. So these the three options are a permutation, right? Or a shift of each other, or a cutting of one gets you to the other. And this one, the first row, no matter how you cut it, you will never reach one of these. Okay, you need to check it by yourself, verify all the options. I'm not going to do it. You can see that there's something really fundamentally different from this than these three. Here you have 3 aces in a row, and here you don't have it. No matter how you cut it, put it in the front, it will never reach this scenario, this order. So when we see this thing, there's a really a mathematical name for it, invariant or whatever, never mind. You know that there's something interesting here. There's something you can do with it. You can use it. What do you do with it? We said if we cut these, we get one to the other. So that's what Alice and Bob do, right? While the cards are hidden, while we're in this scenario that nobody sees it, they cut the deck. Alice takes the deck and cut it. One second, I need my hand. Okay, cut it, put, like, I mean, not a random shuffle, but really a cut. Like choose the bottom of the deck, put it on top. Choose some, 2 cards, 1 card at the bottom, put it on top. She does it a few times. Then she passes it to Bob. Bob also does it. Cut the deck randomly, put the bottom on the top, bottom on top, and cutting is again like cutting this, putting it in front, cutting this, putting it in front many, many times, or a handful of times, whatever. And after doing this repeatedly, then they reveal the cards. They both like flip the cards, and they see which scenario they're in. So they can, there might be in one of these scenarios, in which case they know they have a mismatch, or a cutting, again, some random cutting of this, which is distinguished from the other situation. So they know they're either in this scenario of like or a match, or a cutting of it, or a random cutting of it, which is different than one of these scenarios. But without knowing what happened originally. And that's the whole point. Because they did their cutting randomly and privately, without the other one looking, they don't know what was the order originally before the cutting. And they completely hidden their private inputs. But again, if there's a match, they both like each other. But if there's a mismatch, they don't know who's the one and why. And really, that's the whole example. So it's, I don't know, for me it's exciting. It's a kind of like, I've just learned about it kind of recently, and it's the first time I see like an Mpc in the wild, or in practice, with physical objects. Until now it was more a mathematical thing that we'll see later in this talk. But any questions about that? Like why it works, what's the problem? Yeah. Yeah. So yes, I was the first one who cut the deck, doesn't know it. So the cards are flipped originally, right? He collects them. Bob is looking on Alice, right? She sees she doesn't do anything fishy. She gets the deck hidden, right, upside down. And she cuts it while it's upside down. Okay, randomly. Also, why it's important to cut it randomly? We have time for questions? For me asking questions? Okay. So she cuts it randomly because exactly. If she would have cut in a way that Bob looks at her and see how she's cutting, he can reverse it later when he gets the deck. He can say, no, she did it like this. I can reverse the process. But if she does it randomly and like kind of like without Bob looking, yeah. Okay, nice, good. Oh, amazing. It's like I paid to. Okay. So how do I convert this to a real cryptographic protocol that I can run on a computer? So let's try to think. This is like kind of my addition to the protocol of thinking what really goes on there. So if I wanted to convert it to math and crypto and really algorithms. So what tools, and this is what cryptographers do, by the way. They have like an insight, an idea. Okay, I wish I could have done this and that. And then say, okay, what mathematical tools allow me to do it? What are the building blocks that I need? So first, I need to hide the cards. And hiding is encrypting. Okay, so I have an ace, I have a king. I can encrypt them. This is like flipping it upside down. Like physical flipping is kind of like encryption. You hide your secret. This is what I told you, like you have a cryptographic building blocks or tools. Okay, you need to use, where's the dot there? I don't know. You need to use rounds of communication. Oh, sorry. Because, Alice does something, then pass it on to Bob. Bob does something, then they put it like publicly, they unveil it. So this is a communication round between computers. Okay, we have communication nowadays. Alice is a computer, right? Bob is on a different computer, but they can communicate. Another thing which is kind of non-standard and special, like in this scenario, they need to operate on the encrypted ace and king, right? They have their preference encrypted, hidden, but they need to operate it. They need to concatenate it. They need to put it all together in one deck. They need to cut it randomly. So they need to. This is called in cryptography homomorphic encryption. You have something hidden, but you still can operate on it without knowing what's underneath, right? You work on the cards without knowing what's hidden there. So that's when you can convert it to a cryptographic protocol that does, or cryptographic primitive or homomorphic encryption. By the way, this is another topic that goes very, very into industry very, very strong way. Like homomorphic encryption, also Microsoft has a library about it. Like there's a few startups that work on it. How to work on data without knowing what you're working on. It's a whole topic, a whole talk in and of itself. But it's a tool that exists. You need to use enough randomness, right? So as I said, when Alice and Bob each cut the deck, they wanted to do it randomly and secretly without the other one looking at him, because then they can reverse it if it's not random, if it's not secret, the way they cut. So, okay, using randomness is something we can do in a computer. It's another important thing. And something which is much, much more delicate is maybe relating to your question. Bob is looking at Alice and he wants to see that she's not cheating. But she's cutting the deck hidden, right? She's cutting the deck in a random way without Bob knowing how. But he still wants to be assured that she's not cheating. So if you convert it to a cryptographic protocol, really you want to run a computer, Alice needs to prove to Bob, zero knowledge proof, that she cut the deck in a valid way. She didn't do any fishy cutting, okay, like cutting or shuffling it in a way which is not legal. So she needs to prove that the format of cutting, the structure of the cutting was valid, without revealing how she cut. This is exactly relating to a zero knowledge proof. And it's really like, you will implement it if you want this protocol. Assuring that everything was done correctly. Also, another thing is, who says that Alice put ace and king? Maybe she put ace and ace at the beginning, or king and king, just to mess around with Bob, and to make him leak his preference. So she needs to prove initially that she put the right cards hidden. So she has to give a zero knowledge proof that she has the right format of cards, either ace or king ace, without revealing it. It's kind of nice. Okay, maybe it's nice to me. Well, I'm the only one enjoying it, but it's really nice to me to think, okay, what cryptographic tool I would need there to assure this physical, protocol that I'm looking at you and I see what you do, By the way, a real zero knowledge proof in the real world, I will take the two cards. I will show you, here's an ace, here's a king. Flip them, do like this. And then, go back. So this is a zero knowledge proof. I convince you that I have the right cards in my hand by visually showing it to you. But in a computer, you can't do it. You can't send data to the other one. Look, here's my data. This is what I'm working on. So you have to have a zero knowledge proof for it. And more. Okay, so when you develop a cryptographic protocol, there's lots of delicate points that you need to implement and use cryptographic tools in the right way. But you can convert it into an algorithm or a computerized protocol. And I want to stress that as cryptographers, when you come up with ideas and for a protocol, and you think, okay, here I showed you a protocol, I think it's secure, like I think it doesn't leak my bits, or it doesn't leak Alice and Bob's preference. Okay, sorry for the bit jargon. Okay, so it's like a gut feeling. It seems okay. It seems like secure. It seems like it hides the private inputs. But then you have to come up. This is something that modern cryptography does. Back in the 80s, it wasn't like that. I mean, I wasn't here, but okay, to know. But they tell me like there wasn't any security proofs. It was just like kind of gut feeling. This seems secure. Let's run it. Somebody hacks it. Okay, let's change it. Let's fix it. But in the past 20 years or so, there was a more mathematical rigorous demand because the cryptography got so advanced and so delicate that you needed also to have a mathematical proof that what you invented, like the protocol, is really secure. So you have a security proof that you really rely on mathematical proof to say, yeah, I mean, you can't break it, okay? And you have to make sure that every article needs to come with a proof or assurance that the protocol doesn't leak as it claims, right? Here I claimed I don't leak the inputs. And yeah, this is a very different paradigm that hopefully is here to stay, right? To prove what you claim. Okay, so now let's zoom out a bit. What is MPC? Okay, we might go over a few minutes, but so MPC in general is a few parties, okay, or a few entities, each with his own secret data, and they want to compute some function of this data. Okay, we said the match or mismatch function for the Tinder, whatever example, but in general it could be any function that they define, like we want to compute it together, but again, without this scenario of trusted party, without sending it, which is like a naive solution, saying, okay, we send it to a centralized entity that computes it for us and tell us what is the result, which we're interested in the result. So MPC in general says, give me a function, I want to do this kind of, without a trusted party, kind of computing the same result, but just by communication with each other. Okay, so I don't have a diagram for it, but just without this, right? Communicating between each other directly, but still hiding the secrets, only revealing the output. Like that's the whole promise of MPC. The output and the function, that's all I want to know. Not the inputs of me being revealed, that I have being revealed. Okay, historically, again, it's since the 80s, kind of being researched and developed. And what cryptographers did, they said, okay, any function that you want to compute, I mean, here we said the match and mismatch, but any function you want to compute, no matter how complicated, you can compute in an MPC protocol. You can come up with an MPC protocol for it, but this was very, very inefficient. Like it was kind of like you know, in mathematics, like you have like existence result. Like there exists a protocol that does it. There is a way to hide your inputs, but it's super, super complicated. Very inefficient. One second. Yeah. Many rounds of communication between the parties, lots of computation, lots of data going on, super complicated, like computation. And yeah, not very practical. But for any function, it's kind of like magical. Any function that you want, like we'll see another function soon, but yeah, it's kind of like magic. Specific functions that you give me are, you know, can be optimized. You can do less rounds of communication, less computation. This is kind of like the art of inventing an MPC protocol for a specific function, but still it wasn't like super, super efficient. And specifically in the last 10 years, there was much, much more interest for specific functions, and you know, very specifically like for blockchain, the function of signing a transaction, to do it in an MPC way, like we'll talk about it at the end, but there was a surge of interest in it, and they understood like how it can be practical for blockchain, and this is what we're going to talk about next. Why, like for 40 years already it exists, but now when you have money on top of it, and it's not like just playing with Tinder or playing with some secret data, but really you put money on the blockchain, even it went into academia so much. The people that don't care about money at all, they said, okay, no, there's big interest in it, let's research it, let's have optimized protocols, MPC protocols for the blockchain world. And we're going to see what we're talking about. Okay, so now, okay. Now we're going to the algebraic part. We have 5 minutes, no way. Okay, we need a bit more. But okay, again, before lunch, if algebra makes you nauseous, maybe it's a good time to leave. So you can enjoy your lunch. Very, very basic algebra. Okay, we won't say like just, okay, don't be afraid. Okay, cool. Already, where's the number? Okay, there should be a, where's my X? Why it disappeared? I mean, it was there in the morning, okay. So, okay, that's a shame. I get the first one. So we're going to talk about what do you need, like what secrets you need really, like what's the most important secret you need to have on the blockchain? So you need a private key. Okay, so the private key is a large number. Should be denoted X, so let's move to the, okay. So this X should have been here, but it's just a large number. And the public key, and from, I hope you all know, like from the private key, you can derive a public key, right? So this is the public key is the address that you tell everybody, this is my address, send Bitcoin to this address, right? Here, the blockchain tells you this is how much money you have on your address. The address is computed from the private key. So the private key is X, the public key is G to the X. G is some constant, no matter, I mean, it doesn't matter, imagine it as 7 to the X, whatever. It's just an algebraic computation on X, okay? Like a very simple computation. It acts like exponentiation, G to the X. And this is public, okay? What happened to the X's? So, really a critical thing, a crucial thing in this scenario is that, you know, G to the X is public. It's my address on the blockchain. Everybody can see it. So I don't want, and I, you know, intentionally everybody can see it. I don't want to be able to compute X or anybody to compute X from G to the X, right? This is like something very fundamental. You have your public address, it's public. You don't want to be able to compute the private key, your secret, right, X. So that's known in cryptography. It's called the discrete log problem. You reveal G to the X, you don't leak X. It doesn't leak any information on X. Okay, this can be a shame for the next slides. So let's see if the X is still there. Okay, here it appears. Here is X. Okay, cool. But this is really it's a PDF. How could there's no font for X? Surprising. Okay. Okay, so this is okay, this is just the private key and public key, but what do I do with it? Okay, how do I use my private key in the blockchain world? So I sign a transaction. So, okay, this should have been sign using X. Okay, this the missing part. Everything is missing also there. Use X to sign a transaction. So when I approve a transaction, I want to say I have some fund. On the blockchain, I have some fund of some Bitcoin. I want to transfer it. So I have to use my private key to approve it, right? And this is what I said, digital signatures at the beginning. I approve some public transaction, but using my secret X that only I know, okay? And of course, it shouldn't reveal X. So again, signing using X on transaction should reveal X. Everybody can verify that I'm the one who signed the transaction. So everybody can look on the blockchain, see, okay, there's some public key G to the X. I can, the signature is valid with respect to this G to the X. And again, with the critical point, nobody knows X. I can't stress it enough. This is the only thing that I want to hide, the private key. Okay, let's go back to MPC. Hopefully now the X's come back, so it will be easier. So, okay, we know that we need to keep the X in a secure device, right? Because everybody has, heard about Ledger, or you can generate on an offline computer, generate the X, or on a paper wallet, whatever. You can write it down if you want, if you like old school. But let's try to do it like still in online devices, but in a more secure way. So I want to work with the private key, but instead of working with one private key, or on one device, I want to split it up. So I have two devices. I have my mobile and PC. I generate a number. Again, X is a number, right? So I sample a number on each device. Okay? I think about it as if the sum of the numbers, not as if, exactly, the sum of the numbers is the private key X that I want to work with, that I want to use on the blockchain, but to use as the private key. But the point is that nobody computes X. So each entity or each party or each device sampled his own randomness or his own random input, random integer, but nobody computes the sum X. They don't send it to each other because I want to avoid putting X on a single device. That's the whole thing I'm trying to avoid, to do it in a multi-party way. Okay? The point is that, okay, it's nice. Each one has a number. X is never computed, but I still need to work with it. I still want to say, here's my public address. Here's my G to the X. I want people to send funds to it. Okay, send me money. Okay, send me Bitcoin to my public key. So I still need to generate G to the X, right? And notice I want to generate G to the X of this X because that nobody computed. Okay, you see, so I have some issue here. And luckily, G to the X is a simple function that can do an MPC for it. So the mobile computes G to the X1, G to the local number that he computed, or what's called the local share Okay, this is what's called secret sharing. So you compute G to this own share, send it to the PC. The PC computes the same with this local share, send it to the mobile. Now notice that each one of them knows G to the other value. So you can compute, each one of them can compute this. Okay, this is algebra finally. We have some exponentiation laws, right? Okay, you can verify this formula. So each one can compute this value. And this is G to the X. This is the public key as if somebody knew X and computed the public address from it. But nobody knew X, right? That's the magic. So, you know, very simple magic, but it is. Think about it. I mean, so that's an MPC, I would say, for key generation. In a distributed way or in a split way, we generated the key. And yeah, I'm going to take another minute of your time to tell you this is very, very risky to do it like this. Okay, let me just say before that, because we didn't have X on the same device, so now in order to steal X, the private key, you need to hack both devices, right? Because if you hack only the mobile, so you get X1, okay, you have it, but you have no idea what to add to it, right? And I can tell you more than that. In cryptography, X2 can be negative also. So it can be like, okay, X1 is 5,000. How much is X, really the private key? I have no idea. Like it can be whatever you added to it. So to hack into X or to steal X, you need to hack two devices, this is why it's considered like MPC is more secure for key management. You split it on many devices, you need to hack all of them in order to get a private key. And that's the whole promise of, like, let's say, Fireblocks, like the underlying mathematical promise of Fireblocks. You need to hack all devices in order to get X. Okay. But this simple protocol, I want to tell you, it's not really secure as is. I mean, cryptographers has some work to do on top of it. It's not that simple, because somebody can really mess around with your key here. So if somebody hacks only the PC, okay, the mobile still does the same, but the PC doesn't. He waits a bit. He says, "Let me wait for the communication. I'm a hacker. I want to wait. I don't want to tell you my G to the X2. I wait that the mobile will send me G to the X1, okay? And now I do the following, like a fishy thing, like a malicious thing, that I compute this. Okay, wow, formula. This is the vision. Okay, we're advancing in our mathematical abilities. So he says, instead of sampling X2 and then sending it, let me wait and compute this G to the X2. Right? I'm supposed to send G to the X2. I'm the PC. I'm the attacker. I compute it in this way. Verify my math here. But notice what happened. It's as if the PC chose this X2, even though he didn't know what is X1. Right? The PC just got G to the X1, which supposedly really hides X1, but he could have cheated by computing this G to the X2. Again, not X2 exactly, but G to the X2 by this simple division of G to the some number, whatever, 1, 2, 3, 4, 5, over G to the X1. And he can do it only after he got G to the X1, right? So that's why he waited to get G to the X1 to compute this value. So saying, okay, so what happened? Woody, what's the problem? The problem is, what's the public key now? You can see. I mean, this is what they agree the public key should be, right? My G to the X1 times your G to the X2. But this, because the malicious party, the PC chose this is the public key now, G to the 1, 2, 3, 4, 5. But who chose 1, 2, 3, 4, 5? Who participated in choosing 1, 2, 3, 4, 5? Only the PC, only the attacker. The attacker said, I chose some number. I used your G to the X1, the mobile's public data that I got, to inject my own private key. It's a single point, it's a single private key that I chose, the attacker, to put. And you thought you're running an MPC, right? You thought you need to hack both devices to get a single private key. No, you injected a single private key by attacking a single device. So to fix this, you need to really devise, like I said, a cryptographic protocol that's really in the right order of things. So here, it's not like the mobile. The problem is that the mobile sent this data before the PC chose his data, chose his X2. And to fix it, you need to add a few rounds of communication. I won't go into it, but you can fix it. By adding communication round and some commitment, decommitment, another cryptographic tool, never mind, to fix this. And this is what I'm saying. Like, it's not like you have a gut feeling of security. You need to really prove it. And the protocol I showed you before, you can't prove it's secure because it's not secure. Okay, but after you do the right things, you can prove it's secure, and then you can generate a key, and knowing, okay, nobody controls the key, no single entity controls it, it's distributed between the parties. So now, okay, I really just want to finish for like two more minutes. So we said, okay, you generate a key in a distributed way. It's, you need to hack all devices to steal the key, but what can you do with it? I mean, unless you can sign a transaction, there's no point in it, right? You can load funds on the public key, on the public address, but you really can't sign transactions. So you need an MPC also for digital signing, okay? The problem is, yeah, okay, so we can't just say, okay, we store the private key securely, but we never use it. It's kind of like pointless. So you want to sign a transaction, again, using your private key X, but nobody holds the private key X, again. I'm repeating it because, you know, this is the whole point of MPC. You only hold shares of X, X1 and X2. And for this, I won't even show you the formula, like it's super complicated, and for sure not a protocol. Yeah. We can do an MPC. I told you before, like in the 80s, they knew how to do it, right? Every function that you want to compute, sign a digital signature is a specific function, okay? So there is an MPC for it, okay? Even without storing X, like while it's split between the entities. But the problem is that the formula for signing is very complicated. The protocols from the 80s would have taken you like, I don't know, hundreds of rounds of communication, like infeasible amount of computation. Nobody even tried to think about how to implement it. It was super complicated until the interest of Bitcoin said, okay, we need a practical protocol because we want to compute the signing function in a MPC way. It's a specific function. Let's look at its algebra. Let's devise a cryptographic protocol to do it efficiently. And really, the Bitcoin, the blockchain world really pushed this interest from the academia. And in 2016, there was a few articles started, 17, of this efficient protocol, really like 10 rounds of communication, really reasonable amount of computation to compute in an MPC way between the devices' signature. And yeah, it's a few rounds, but it's complicated computation. Still, it's the computation is a second of computation. It's not like something 2 hours of signing. It's a second of computation to sign between a handful of devices that you split the key. And yeah, that's it. I mean, that's again what lies in the mathematical part of Fireblocks. Like that's where I help them implement this thing. But on top of it, I mean, there's lots of other stuff. But this is the math. Okay, so what do I have to say just to conclude? So MPC wallets. So you want to. They're a bit more secure than if you know multi-sig wallet, because in my mind, I don't know, a bit more also, I would say, like modular. They allow you to have more flexibility. And you keep the security of the private key not on a single device, on a few devices. Okay, but you need to do, the price for it is to do some complicated math. I mean, not super complicated, but if I can understand it, so can you, but it will take some time. Yeah, and there are different protocols for it. Like, so the digital signature is a single formula, but there are some different protocols, like less rounds of communication, more computation, like different features of the protocol. Okay, these are differences. I mean, there are still articles coming up today that are changing the protocol for the same function, the digital signature, with different features. But that's ongoing research and advancement in the topic. And okay, just to give you a feeling. So what you need to remember, I hope you remember the example with the cards. It's really cool. Think about it. Play it with let your kids play with it. And I hope you understand that, or got the feeling that MPC can be used to secure in a better way private keys than storing them on a single device, but on multiple devices, but still using them as if they were on a single device. Like that's the point. This is the use case for blockchain. And yeah, that's it. And thank you for your time. And bon appetit. Questions? Yeah. Yes. Yeah. So the question is, if you sign in MPC way, there's some entity, one of the parties that gets the signed transaction, right? And it needs to broadcast it to the network. So again, depends on the architecture, but yeah, let's say it's one of the parties. So he can reject. He can say, okay, I don't want to publish it. Okay, so what can happen? It's a DDoS attack, right? You're saying one of the parties is saying, I don't want to participate. Not even just broadcasting. You can say from the beginning, I don't want to run the MPC. Alice says, I don't want to play with Bob. I don't want to continue this interaction. It's always legal in cryptography to say you can stop interacting. Also, not broadcasting the transaction is stopping interaction, or not even doing the first round. And that's something you can't avoid, or just the computer shut down because somebody, the electricity went off. You can't avoid it mathematically. So this is like an infrastructure, architectural thing to come up with the solutions. But it doesn't pose, like I would say, a leakage of secrets problem. It's more of a kind of approval of, I can sign something, you can't sign something else. You can't, this malicious party, he can say I broadcast or not, but not I sign something else or I prove something else, because he did it in MPC way between the parties. So there is no mathematical, at least, research about it. Like it's kind of like your decision of, again, architecture, the way I say it. And that's why, you can devise the saying there's a fallback computer that if this fails, then this, or if this, the attacker prevents this from working, maybe I send it. But he can't change the data, or change the signature, or get the private key. You can just say, do or not do. Yeah. Yes, another question?
Yeah, it sounds like
Magic. Like
you have a way to deal with multi-sig transaction with 3 out of 5.
Right, of course. Yeah, so what I presented here is what's called a 2 out of 2 scenario. The two parties want to sign or to interact to get the output of the function. But in general, it can be much, much more like any reasonable, what's called structure of approvals. So it can be like you're saying there's 10 entities, but any 4 of them can sign, or any 4 of them can give me the output. It's called threshold signatures or threshold cryptography. You need some threshold of numbers of users to approve what you want to do or to get the output of the function. It's much more general, yeah. There are many options, and yeah, you need the different protocols you have to be careful about. Yeah. Yes. Yeah. It's no. It's maybe I didn't stress it enough. So there's the signature that we're trying to compute is the signature that all the blockchain works with. We don't change it. It's not like even in a multisig. If you know, in a multisig, you're saying no. I need a script to verify it. I need something changing on the blockchain side. Here we're saying the opposite. We want to change. We want to keep the same signature public. Everybody think. Or every validator on the network, every node, think that he saw a signature from a single private key on a single device, but we, in the background, do it in an MPC way between the devices computing this MPC protocol. So it's completely like kind of the opposite way. They're saying everybody sees the same as they should expect, but I'm doing different in the background in a split way. Yeah, so it depends again on your model of of a company that you're coming up with, but you want to back up maybe your shares. X1 needs to be back up or exported to an offline device if you want. But I wouldn't. If you're running an MPC protocol, I would advise against computing the X on a single device. Like don't send to each other the X1, X2 because if an attacker is there and he knows both X's, X1, X2, or all the shares of your X, he can compute X. In this single point of failure, you're afraid of. You're trying to prevent any point in time that X sits on a single device. So I would say maybe encrypt it and send it to another, have a backup for it. Like there's different backup scenarios, and this is another research we're doing at Fireblocks and advancement there. Like how to back up in a reasonable way, which doesn't, pose any new risks on the private key. Yeah. All of you all know everything, huh? Okay. Cool. Okay, thanks a lot.